Congestion control is a complex problem. In this video, I will motivate this particular problem. The actual details we will see in another video. A quick recap. These are the services that TCP provides. I will let you glance at it. And these services are provided in the context of the sliding window protocol. So this picture should help recollect what sliding window protocol is. Nonetheless, let me ask a question to ensure indeed you remember. So if W is the window size in packets and MSS is the maximum segment size, that is the segment size that we are using, the throughput is given by the window size into the segment size divided by the round trip time. By the way, this is an approximation because there is transmit time to also consider. So if W is large, you can ignore the transmit time. So what is the problem of congestion control? Suppose you have a TCP connection between a process that is running on this host, let me call it host A, over many routers. At the other endpoint is this process that is running on this host B. So the question is, what is the throughput that can be achieved by this particular TCP flow? Now this is a function of many factors. These routers are also serving other flows. And it is not that all these other flows are also taking the same path. Some flows may end in like this, some flows may go like this, so on and so forth. Not only that, at any given router, the number of flows that pass through it is going to vary with time because flows end, new flows start, so on and so forth. Now these flows could be TCP or UDP. The difference is important because UDP doesn't do any congestion control. It just blasts away the data. Whereas TCP tries to ensure some amount of fairness. These issues will become clear later. Also, the link bandwidths that interconnect the routers could be different. For example, this could be a 100 Mbps link. This could be a 10 Mbps link. This could be a 100 kbps link, so on and so forth. So the end result of all this is the throughput that a flow achieves is governed by all these factors and it is going to vary over time. Now we are doing a sliding window protocol where the throughput that you are going to achieve is a function of this window size. Now, if you want to use the sliding window protocol, you need to select this W such that you get a fair share of the throughput. Let me illustrate this point through this example. Suppose your TCP flow is going over these routers R1, R2, R3, so on, and I'm also indicating this link bandwidth by this number R1, R2, R3, Rn. Now this router, let's say, is supporting K1 flows, supporting K2 flows, and so on and so forth. And let's also assume that these flows are TCP flows. Now what is your share of the throughput at this particular router when this link bandwidth is R1? So if fairness is honored, the throughput that you will get is basically R1 over K1 because this link throughput bandwidth is going to be shared across all these flows. At this, it is going to be R2 over K2. At this, it will be R3 over K3, so on and so forth. Throughput is a single number. You're not going to get these distinct numbers. So what you end up getting is basically the minimum of all these. We will look a little bit more into this issue a bit later. So this is what you're going to get. In fact, you may get more than this because for these other flows that are going through it, their bottlenecks will be different from your own bottleneck. In other words, those other flows may not be making use of the full share of their bandwidth at a given router. Now, how does one estimate W so that you get this particular number? Now, if your estimate is small, you're going to underutilize. In other words, you're not making use of all the available bandwidth. On the contrary, if you estimate large, thereby trying to get the best possible throughput, you are going to congest the network because you are pumping more data than the network can handle. And as if these problems are not enough, this W itself will have to vary over time because some connections will end, some new connections will start along the path. As you can see, determining W is not at all an easy task. This underutilization is not desirable, but more importantly, overestimating W is dangerous. It's very easy to push a network into congestion, and it is not so easy to get it out of congestion. You can relate to this because you must have experienced traffic jam. It's very easy to cause a traffic jam, but getting out of the traffic jam takes time. So that is where the term congestion control arises. You basically want to prevent these sources from sending too much data too fast and thereby congesting the network. Since we are making use of the sliding window protocol to send data, let's spend a little bit of time understanding what this protocol does. So this is a quick summary. So in sliding window protocol, we use the network as a pipe and you determine the capacity of this pipe, which is basically the bandwidth delay product, and then you're going to fill up this pipe with this data. This is what we call steady state or equilibrium. Once the pipe is filled up, as you remove one packet from the pipe, you're going to add another into the pipe. Now tell me, who gives you the information that the packet actually has been removed from the pipe so that you can add another? ACKs, right? So ACKs help clock out data. So this is called self-clocking. So sliding window protocols possess this very interesting concept called self-clocking. So let's see this in a bit more detail.